In this class, we are going to cover section 1.7, how to use a fitting model to data. So when we model data, we're trying to find a function that matches the data being studied. In our cases, we're looking for a line that fits the data. Usually this line is not going to perfectly match our points, such as after you know some x and y value in a coordinate plane, you will have some scattered data, look like this way. And then we're trying to find a line that fits most of the data. So this one, an example, is not a perfect graph. This may be a good line for this data, but we know that this 9.2 is not going to be a good line compared to 9.1. So we're trying to find a line that is the best fit for all of the data on this coordinate plane. We can use technology to help me to do that. Later I'm going to explain it to you how to use Desmos to help us to find that line. Before that, I want to introduce some concept about correlation coefficient. So what is correlation coefficient? Coefficient. So correlation coefficient are used to measure how strong a relationship between the two variables. The formula return to the value between -1 and 1. So for example, by definition, if it's positive 1, it indicates a strong positive relationship. So that means this is an ideal scenario. So you will see a line. All of the points, they line up. They can just form a line. Like this example. This is a positive relationship. So on the other hand, a negative 1 indicates a strong negative relationship. Oh, should be a P, not G. So the graph might look like this way. So you can see this point almost perfectly aligned to become a trend line that fits all of the data. So this is the coefficient of this one. Coefficient, we use the letter R. I forgot to mention that, sorry. So this R is going to equal to -1. And from the upper example, R is going to equal to 1. So for the correlation coefficient, the range for R has to be between -1 to 1, but in most of real life example, in reality, it's very hard to find two variables that are so strong related so that it's equal to 1 or -1. So most of the case, you will see the two variables look like this one. They almost look like a 9, very close to 9, but not exactly. So we will find a 9 in between it. So this, in the third example, is most likely the correlation coefficient is going to equal to somewhat maybe 0.9 to 0.8. So the number is still very high because this is increasing, as you can tell. So I can see that it's still an increasing relationship. Another example would be a weak negative relationship. So this is Y, this is X. You can see, okay, the line is very scattered. but you barely see that this is can form a 9, but I can still make it. Okay, looks like very like a 9. Oh, this is still positive. I want to use a negative example. Let me erase that. So maybe here you can see a 9 very scattered away, but maybe we can still find a 9 that in between that, okay, indicate the chain 9 of these two variables. In this case, our r is going to equals to maybe negative 0.2 or maybe even lower, negative 0.1. So the correlation, the r value is not indicated the slope. The slope could be really flat, but you can have a big r value, such as this one. Maybe some of them are off the line. Something look like this one. You can see a line. They fit all of it. So in this one, r maybe equals to 0.9 because almost maybe just two data that is not on the 9, the chain 9 that we drew. But you can see that, okay, most of the data fit in those 9, except for maybe 1 or 2. So this is really strongly related, the two variable, but it's a negative relationship. So that's why it's a strong negative relationship. So the r value is equal to negative 0.9. So here is the example that we can find from the textbook, shows us that, hey, the correlation coefficient value, for example, the first one is really strongly, you can see just 1.9. So that's why the r value is equal to 1. And then when it comes to the second one, you see 0.8, you can see a little bit far away from each other, but it's really clear that the chain 9 is still a straight line. So that's why we define it as a 0.8. Now, look at the second row. You can see that the r value equals 1 is equals to 1. So that means x and y, those variable, they can form a straight line. But you can tell that the slope could be very steep or flat. They all equal to 1. So that means the correlation coefficient has nothing to do with the slope. It's just related to how the point like form a line, how well they form a line. So in the third row, you can see this is r value equals to 0, that this point they just scattered. They might form a different shape, such as a square or look like a moon or a circle, but it's not a line. So that means the relationship they have is not linear. So in this case, we will consider the r value is equal to 0. So here's an example. I'm going to show you how to use a Desmos to help us to find that line. So the table below shows the number of cricket chirps in 15 seconds and the air temperature in degree Fahrenheit. So we need to plot this data and determine whether the data appears to be linear related. So the first step is, let me pull out a decimal graphing calculator. So one thing we need to be careful when we're finding the decimal. For me, the first thing that I search to find is the decimal scientific calculator. We don't want that. We want to find the decimal graphing calculator. And then we will pull up the first one. Okay, so how do we enter the chart? What we're going to do is from the upper left, you see the plus icon, which is we want to add items. So we want to add a table. So S1 is going to be our dependent variable. Y1 is going to be X1 is going to be our independent variable. Y1 is going to be our dependent variable. So we want to know that if the chart is, what do they want to find? So from the textbook, they want us to determine whether these two appears to be linear related. So that's what does that means. We want to see if the chirping, the frequency they chirp, is that going to be related to the temperature arising or not? Okay, so now let's plug in the data. So S1 is going to be all of the data that we found for the chirping. I'm going to pause the video and type in input all of the data in it. You can also do it by yourself, open a Desmos. Okay, I just finished putting all of the data in it. So X1 related to how many times a cricket chirp in every 15 seconds. Y1 is the temperature in Fahrenheit. So now the next thing we're going to do is going to type in, look at the header is X1 and Y1. We want to know how X1 and Y1 linearly related. So remember what is the basic linear function? Is Y equals to mx plus b, which is the slope times the x variable plus the y-intercept equals to our y. So in here, we got y1, and then we open the keyboard and choose the ABC and choose that approximate icon. And then we want to have A, or you can use M. We can use mx1, which is the slope, x1, and then plus B, trying to find the y-intercept. Okay, so here, the regression give you the parameter. In our case, M is equal to the slope is equal to 1.1438. B, the y-intercept is equal to 13.2859. And the R value is equal to 0.95. The R square is the R and then square. Okay, so here, I'm sorry, I didn't show you the graph. I'm going to hide this first. So at beginning, after we type in, input all of the data, the point is already plugging in the coordinate plane. So maybe I can change the color. Okay, and then after typing the function y, because I assume that okay, the trend line is really obvious that this is look like a straight line. So that's why I'm going to use a linear model, trying to find how linearly that these two variables related. So I type in y1, I have to use y1, I can use y, because our dependent variable is y1, and then independent variable is s1. For example, let me change that. If I change this to y2, the line is not going to show. If I change that to x2, so in the bottom here, I also need to change that to x2. Then they will show you the 9. So 9 is in the black line. So here is our linear model. So basically, in your answer, they found, hey, okay, what is the linear model? So what we got is y, which is the temperature, is 1.14318 x times at 13.28. So this is our 9. So we just need to substitute that into our function to find the linear function. So what can we do after we know the function? So first of all, you need to remember that x is the frequency that cricket chirp in every 15 seconds, and y represent the temperature in Fahrenheit. So in that case, we can use it to predict the data. For example, if I tell you that, okay, the cricket chirps 13 times. So which 13 is not on this graph. So can you estimate the temperature? Well, the answer is yes, because what we can do is we can type in a function, which is fx equals to our mx plus b. So this is going to be our function, which m is going to equal to the slope that we found, which is 1.14318, and b is going to be the b-intercept that we found, which is b equal to 13.2859. And then we're trying to find, okay, the cricket chirps 13 times, which is f of 13. So the output is 64.57 Fahrenheit. So that gives us that, okay, we can use this to predict what the temperature is going to be. So that's what the fitting model for. You don't really need to use Desmos. I know that there are so many online free tools that they can help you to find out the fitting linear model after you put in the two variables data in it. So that's one way to do it. You can play around it with your homework. That's it for today's class.